Okay, we're going to look at sketching cubic graphs, calculus part 5 here, and let's just start off here. It says that f prime of x is the gradient of the tangent to f of x at any point of f. So say this is a function, and it's a cubic function because it's x to the power of 3, and if you solve it, you make it equal 0, you can get 3 different roots. 1, 2, 3, a line will hit it in 3 places. But let's look at some things we have to know about it. Well, one of the things we have to know is, where is this thing increasing? And you can see, as I'm moving from left to right, I can see that it's getting bigger and bigger and bigger until it gets to here. And if I took a line and pushed it against it, it would have a positive gradient. We say it's increasing to the left of P. All the way here, it's increasing. And then it's not increasing here. You probably know the word for it. But it's increasing to the right of Q. So that's where it's increasing. And that's when the gradient, f prime of x, if you pick any x value in here, the gradient will be positive, greater than 0. But between P and Q, it's going to be negative. It's going to be less than 0. And I can see that it's decreasing. It's getting less and less as it goes to Q. Okay, that's an important thing to know about. The next thing that's important to know about is where it equals 0. If f prime of x equals 0, that means it's right at the top or the bottom. We call this a local maximum, and this is a local minimum. But if you make f prime of x equals 0 and you solve, you'll find the x values of something called the stationary points or the turning points. The graph stops going up and starts going down. That's what happens at P and Q, or vice versa. It starts going down and starts going up like that. Okay, what's important here? P is called a local maximum, even though it's a bit bigger up here, but it's a local maximum. And Q is a local minimum, the lowest point in that part of the graph. And S, that point there is special. Its gradient's negative there in this picture, but what makes it special is it's the point where it changes from, this is called concave down, like a hat, and this is kind of like a cup. It's called concave up. That point there is called a point of inflection. Now, what's that about? Let's take a look at it. Do you know if we take the derivative again, and if we put a value in there, we take the second derivative and then take that value and put it into that function, we'll get where it's concave up. If the second derivative at any x value is greater than 0, then it's concave up there. If it's less than 0, if it's negative, it'll be concave down. So here it must be negative, it's concave down, and there it must be concave up. Now, if we let it equal 0 and solve for it, we'll get the point of inflection. Do you know if you let f prime of x equals 0 and solve, we'd get these two x values where it turns, and that's what you always do. And later on, to get maximums and minimums in calculus, you take the derivative, make it equal 0, and solve for x. But if we take the second derivative and make it equal 0, we'll get where concavity changes from concave down to concave up, or vice versa. It's good to know, Mr. Autry points it out, it's exactly halfway between these two turning or stationary points. Well, that's our introduction to the main ideas of cubic calculus.